This is a lesson in a series of lessons introducing bipolar junction transistor-based amplifiers. To date, we have worked through large signal problems, DC biasing problems, small signal modeling, and some sample problems, and now we arrive at this fourth item where we will be looking at the three topologies, amplifier topologies, the common emitter, common base, and common collector topologies. Before diving into these three topologies, we want to look at just the general amplifier stage configuration that will be common to all of them. So I've drawn three of them here. These are going to be valid for the three configurations. So regardless of whether it's common emitter, base, or collector amplifier, this is kind of like the basic architecture of the amplifier. On the left here we have purely resistive biased amplifier stage. So through negative feedback, we've seen this in the biasing section of these lessons, that RE can be used to stabilize the current and desensitize the DC operating point from beta, from the forward current gain of the transistor. This first one is for single supplies, and we have a second one here in the middle that is set up for bipolar supplies. And then lastly, we have an example of a bipolar supply amplifier, but that is biased through a current sink I right here. And we'll actually be using this one. We're not going to lose any generality in our results, but it'll just be more efficient to go through the derivation of these three amplifiers using this third configuration. Okay, so we'll be using the current biased setup. And so what I have here, well, first of all, you notice that I've not defined inputs and outputs. Let's do it over here. Inputs or outputs. I've just labeled XB, XC, XE. And the type of amplifier that we have is going to be based on where we connect the inputs and the outputs. So I've redrawn this bipolar current sink biased amplifier stage 3 times here, and each one represents the one of the three configurations, beginning with the common emitter on the left. So notice that the input for the common emitter is the base, so we show a voltage source VI, our signal source, our input, connecting to XB, terminal XB. And the output is taken across the collector via this output coupling capacitor CC, which is a DC blocking capacitor. We then connect to the emitter terminal XE. We connect a resistance RE to ground. For the center, for the common base configuration, which is in the center here, the input is actually the base and the output remains the collector. So now we ground the terminal XB and we connect our source input to the terminal XE right here. Now you notice we add in a resistor RE in series, and we'll consider that shortly when we analyze this circuit. And then lastly, we have the common collector on the right. There the input is back to being the base, and the output now is taken at the emitter rather than at the collector, and there is no connection to the collector terminal XC. Let's begin analyzing the common emitter amplifier. We will draw the small signal model circuit, which means we're going to get rid of all of our DC sources. We will short all of our coupling capacitors, and we will replace the transistor with an appropriate model. Now we can use either the pi model or we can use the T model. I'm going to choose to use the T model in this case, and maybe we can explore using the pi model somewhere along the way here. Notice that the current source goes away. It becomes open when we look at the small signal model, right? Because it's DC. The capacitor CE gets shorted, and so therefore what we really have is an external R capital E in series with our transistor model emitter resistance R little re. I'll draw a dotted box here around our transistor T model. Okay, T model. Here the current will be alpha IE, and of course IE is the current flowing through little RE. And here we apply, okay, we'll have a grounded RB, but that will be insignificant to the amplification because we have a voltage source VI. Let me actually draw a voltage source here. So the output voltage is across the collector, little VO. Now, what we have now, we have a voltage VI that is applied directly across these two RE resistors. That's the first thing to note. So regardless of what's going on with the current source, because there's a straight connection straight through from VI to the base, we are applying VI straight across little re plus big RE. So as a result, we can write immediately IE is equal to VI divided by little re plus big RE. We can write that the collector current, which is this current source, is going to be equal to alpha IE. And we can write then that VO is going to be equal to minus, right, because current is being sourced from the ground flowing through these resistors RC and RL. It'll be minus RC in parallel with RL. Both those are grounded, right, times our current IC. Right, but IC is alpha IE. And IE is 1 over little re plus big RE times VI. So we can rewrite this as AV, which is VO over VI, small signal, is equal to alpha or minus alpha RC in parallel with RL divided by little re plus big RE. This looks very familiar. It's in fact what we found for the MOSFET common emitter amplifier. Of course, we had a drain resistance, not a collector resistance. And our RE, little re in the case of the MOSFET amplifier, was 1 over GM, if you recall. So here it's a little different. Although let's remind ourselves what little re is, right? Little re is equal to, you can always remember this as the thermal voltage divided by the current flowing through that leg, the DC current, so it's IE, right? Which is equal to V thermal over IC divided by alpha, and that is nothing more than alpha over GM. So essentially we have the same thing, and alpha is about 1. So this expression for voltage gain is essentially the same as what we had for the MOSFET. The one thing that's different is the alpha. In both cases, the alpha that's here and this alpha here would have been 1 for the MOSFET amplifier. Now we can express a few other things. We can say that, let's see, RO is going to be equal to simply RC. That's pretty apparent here. Now we're ignoring the output resistance of the transistor. In other words, the early voltage that that shows up as an RO across from the collector to the emitter. We're leaving that off for now. Okay, and then lastly we need to find what is RI. Sorry, that's a big RO. RI is equal to, it's going to be VI over II. And that will be, we'll have VI over, what current will we have? We'll have VI over RB, so that's one source of current, plus we're going to have IE divided by beta plus 1. Now you might think that all of the current that is going in this path here, the VI over little re plus big RE, is going to come from the base, but that's not the case, because most of that current is coming through this current source here. In fact, if beta is 100, then 99% of that emitter current is coming from the collector, and only 1% is being supplied from the base. And so we can instead write that the current through the base, IB here, is simply IE divided by beta plus 1. Now we have that IE here is what? IE is VI over R little re plus big RE. And so now we see that, and I'll clean this up in a minute, we see that what we have is 1, the VI's cancel, we get 1 over RB plus 1 over beta plus 1 times RE plus big RE. Alright, and what that is basically it's RB in parallel with this resistance, beta plus 1 times the two RE summed together. So let me erase all of this, and we will write this now as RB in parallel with beta plus 1 times little re plus big RE. That is the input resistance. So, for instance, if we found that this was 50 ohms, little re was 50 ohms, and if we had made big RE, let's say 250 ohms, and beta was 100, then this term here would be 300 times 100, so that would be 30 kilo ohms. Okay, so just to give kind of an order of magnitude of the input resistance. We won't see the same high input resistance that we saw from a MOSFET amplifier. That's just not going to happen because we don't have an insulated gate like we did with the MOSFET. Okay, so now let's return to our three circuits, and we'll look at the common base. Okay, so for the common base, I'm going to draw the small signal. Let's say common emitter, small sig circuit. Now we'll do common base, small sig circuit. So again, we have the grounded collector resistor. We have our output still is across the collector. So we have our load there. We have our current source. I'm still going to use the T model. And now The input is going to be in series with little RE. We have a large RE, and then we have VI, little VI. And on the base, we have the base capacitor is shorted now, and so it's shorting the base to ground. So that's what we have for the base right here. So now let's look at the emitter current, IE. IE is actually going to be, again, equal to VI, or due to VI applied across the two resistors, but notice that the polarity is opposite. Now we have minus VI over the sum of these resistances. Okay, and VO is going to be, as before, RL in parallel with RC times this alpha times IE. Alpha times IE, but IE is minus as this term here. So we can rewrite this as minus VI over RE, little re plus big RE. Let me clean this up. And we'll have minus alpha times the ratio RL parallel with RC over little re plus big RE. All of that, oops, all of that times VI. There we go. So we can say, therefore, that the voltage gain, AV, is equal to same expression as before, except it's not inverting. Oops, I made a mistake. We have a double negative, right? Because of the current IE being minus VI, that minus cancels the minus that we have due to the current flowing in this direction and producing a voltage drop from ground. So we have a non-inverting amplifier. Same gain expression as the common emitter amp, but non-inverting. Now what about, well, RE is going to be the same as before. We'll have little RE is equal to alpha over GM, or just VT over IE. Alright, now the output resistance, RO, will be equal to RC as before. That has not changed. Now what about RI? Well, now RI is going to be easier to find actually than what it was previously, because this current source is flowing straight to ground, and this terminal here is at 0 volts, and so truly all we have between VI and ground are the two RE resistors, and so we're going to have RI is equal to little re plus big RE. So comparing that to the common emitter, this is roughly beta plus 1 smaller. Okay, so if we want a low input resistance amplifier, the common base is the amplifier of choice. Okay, lastly, let's look at the common collector small signal circuit and the gain, the input volt resistance, the output resistance. Again, we'll draw our circuit, small signal circuit. Okay, alpha, a little IE, a little RE. Now, in the collector, we mentioned that the resistance RC is optional here, and it comes into play because it'll affect the operating range, the voltage compliance range of the transistor. It also will help to spread power dissipation, heat, being generated in the transistor out to that resistor. But it doesn't change the small signal voltage gain. So I'm going to leave it off for now, or I'll put it in dotted, but it really has no effect. Okay, the output now is connected straight to the emitter. So this voltage here, the connection between little RE and R load is V out. And we have a connection between the emitter and our input, VI. Okay, the current that's flowing through the emitter, IE, is simply going to be equal to the voltage across it divided by the total resistance. So we have VI, and it's going to be applied across little RE plus RL. And so the voltage VO is going to be equal to RL times that current. So RL will actually be RL over little RE plus RL times VI. So let's rewrite that. AV is equal to RL over RL plus little RE. Now recall that if, let's say for instance, if IC is equal to 10 milliamps, then little RE, which is equal to V thermal over IC, is going to be approximately, because I'm going to ignore the alpha, it's approximately equal to VT over IC, which is going to be 25 volts, over 10 milliamps, or 2.5 ohms. Okay, so if RL, for instance, is equal to 1K, then we'd have that AV is equal to 1,000 over 1,002.5, right? Which is, 0.99, probably close to 999 or 998. Okay, so gain very close to 1. Now what about the output resistance? Well, let's look first at the input let's do output resistance. Output resistance. Now we define the output resistance, actually in all these cases, but I didn't specify it before, when VI is equal to 0. So we turn off the input, and what we do is apply a test signal. It's like a test signal at the output. So we'd replace, here, let me draw it over here. So in this example, we would have RE, little RE, and then we have no R load now. Instead, we're going to connect a little test current, and here we turn VI off, 0 volts. So what is the voltage that's generated here? This voltage is simply going to be RE times IT. And so, it doesn't matter that we have this current, because this current, whatever it does, is going to flow right to ground. Okay, so it has no bearing. So we find that the output resistance in this case is simply going to be equal to little RE. Now this will be a little bit different when we have an input resistance, a source resistance. So for instance, if we look at, say, what about when R sig is not equal to 0? So in other words, we have R sig. I'll call this V sig. And then we have RB. And then our model is that we have RE, little RE, and this goes out to our test current source, IT. Okay, what is the input resistance or output resistance at that point? And there it becomes a little more complicated. I won't solve it right now, we'll look at this later. But it turns out that the output resistance will not only be due to little RE, but it actually will be due to R sig. Okay, well, let's finish this up. We looked at the output resistance. What about RI? So for RI, we're again going to look at what is the RI is VI divided by II or IB. So VI divided by little IB. And this is going to be VI over IE divided by beta plus 1. And so we will have RE, what we'll end up with is RE plus RL divided by, times beta plus 1 times RE plus RL. Maybe I should derive that fully. Let me go ahead and box this and we'll go back to deriving it over here. So let's do it here. What we'd have is IB is going to be equal to IE divided by beta plus 1. And IE we found to just be equal to little VI over the two resistors in the emitter, little RE and then the load. So therefore we can say that RI, which is VI over II or IB, is equal to little VI over, and now we have little VI over RE plus RL, and that whole thing divided by beta plus 1. When we're all done with that, the VI's cancel, we end up with the beta plus 1 times little RE plus RL. So we see that the input resistance is actually a function of the load that's connected. So that's kind of different. So we can't actually say what the input resistance is without knowing what kind of load we have connected. But typically, the load will be higher resistance than little RE. It might be on the same order of magnitude, but typically it's not going to be a lot smaller. So our load will have the more dominant influence on the input resistance. Okay, I think I will stop here because this has introduced or gone through the basic analysis for gain, output resistance, and input resistance for each of these amplifiers, and then maybe pick up in a separate lesson where we will just work some example problems involving these three types of amplifiers.